What's up, everybody? Welcome to lecture 22 of trig. Today we're going to go over section 4.1 and a little bit of 4.2. To start off with, let's look at this definition of complex numbers. So what we've got when we're talking about complex numbers is this thing called the imaginary number. It's the square root of negative I. The square root of negative 1, and it's represented with an I. Just because mathematicians got tired of writing square root negative 1 over and over and over again. So we denote it with an I. And what a complex number is you take these two different values, two different real numbers, A and B. And you say, I want to add A to I times B. This is going to be a complex number in what's called standard form. And there are other forms we might write complex numbers in, and we'll talk about those later. But for now, we're going to just talk about standard form. So this idea of a complex number is saying, hey, I want a real number, and I want an imaginary number. Not the imaginary number, a imaginary number, an imaginary number. The difference here being that the imaginary number is the square root of negative 1. An imaginary number is any real number times I. Just a distinction here. So we've got this complex number. It's a real number plus an imaginary number. And in the case that our B, the number that I is being multiplied by, in the event that that's 0, well, then our complex number is just equal to that real number. And we say it's a real number. It's just equal to A. In the event that our real number is equal to 0, well, then our complex number is just equal to the imaginary part, and we say that that is a pure imaginary number. Now, a little bit on vernacular here. I might from time to time say the real part or the imaginary part. What I mean is the part that's not multiplied by I or the part that is multiplied by I, just as a distinction here. Okay, well, these things are numbers. We're going to want to know how to add and subtract with them, and later how to multiply and divide with them. So let's look at how that works. If we're going to add and subtract complex numbers, we're just going to do that to the distinct parts. If I have a complex number plus another complex number, what this whole thing is going to be equal to is the real parts added together plus the imaginary parts added together. So what does that look like? Well, we've got a complex number plus a complex number. And notice here is just the real part of those numbers added together. And here is I times the imaginary part of those numbers added together. Similarly, if we subtracted them, except notice there's still an addition here. Why is that? Well, it's because of the way this breaks down, right? Let's say we removed the parentheses, because we can do that. It's just addition and subtraction. We were to rearrange things. C here becomes negative. D here becomes negative. So we're going to have positive A plus IB minus C minus the imaginary number times D. So when we rearrange everything, group the real parts and the imaginary parts together, that addition stays there, but these have subtractions within those parentheses, within those parts. So let's look at two different examples. The first example is the complex number 1 plus 2i minus the complex number 4 plus 2i. So we want to find out what this comes out to be. So let's do that over here. Rewriting it, we've got 1 plus 2i minus 4 plus 2i. We can distribute that negative all the way through and drop those parentheses like I was saying a second ago. We're going to have 1 plus 2i minus 4 minus 2i. You're going to want to group the real part and the imaginary parts together. So this is going to become 1 minus 4 plus 2i minus 2i, where we can bring that imaginary number I out. So now we're going to have negative 3 plus I times 0, which is just equal to negative 3. Okay, so let's try this next one. Notice here, now we have a subtraction inside, right? Now we have 4 minus I. What happened? I thought it had to be A plus I, or A plus I times B. Well, this still works, right? B could be negative 1. And if B is negative 1, well, that's going to be the same thing as subtracting I. So let's do that really quick. Three plus 2i plus 4 minus I. Well, we can drop those parentheses. And when we do, we're going to get 3 plus 2i plus 4 minus I. Now we're going to group our real terms and our imaginary terms together. We're going to have 3 plus 4, that's our real part, plus 2 minus 1, that's our imaginary part. Doing the arithmetic, we've got 7 plus I. So, the answer to our second example problem is just 7 plus I. Pretty straightforward so far. So let's look at multiplication division next. Alright, so to find out how complex numbers multiply, I thought we'd work it out like it's a normal polynomial. Just actually work it out on the board and prove what this thing is going to be equal to. Alright, now to do that, we're just going to, like I said, treat it like a normal polynomial. We're going to say a plus bi times c plus di. Now, if this were a normal polynomial, we'd want to FOIL it, right? So let's do that. A times c plus di plus bi times c plus di. Well, this is going to come out to be AC plus ADI plus CBI plus BDI squared. Well, notice something funny happens here. We've got I squared, right? And just a minute ago, I said I is equal to the square root of -1. So I squared, it's going to be equal to -1. So let's see what I'm saying. What I am saying is I is equal to the square root of -1. So I squared is going to be the square of the square root of -1. Well, if that's the case, then I squared has to be -1. All right. Well, then that means we can rewrite this as AC plus ADI plus CBI minus BD. So let's group those real numbers and imaginary numbers together now. When we do that, we've got AC minus BD plus I times AD plus CB. Okay? So that must mean then that the multiplication of two complex numbers, this thing up here, it's just going to be equal to A times C minus B times D plus I times A times D plus B times C. All right, well, let's look at some examples then. Since we've got this, we've worked all this out, let's check out these three examples really quick. What we've got for this first example is the complex number 2 minus I times the complex number 4 plus 3I. All right. So 2 minus I times 4 plus 3I. Well, this first value is A, right? Our second value is B, and that's going to be equal to -1. Why is that? Because it's minus I, right? So it's like saying B is -1. Okay. This 4 here, well, that's our C. And this 3 here, that's our D. So now we can just throw it into this. So what we're going to have is 2 times 4 minus B times D. B is -1 times D, that's 3. All that grouped together, plus I times A times D, that's going to be 2 times 3 plus b times c. So that's going to be -1 times 4. So all of this is going to come out to be 8 plus 3 plus I times 6 minus 4 . This is going to be 11. This is going to be 2. So we have 11 plus I times 2. So why is that? What happened here? Well, we went through, we identified what our A, B, C, and D were, right? A, B, C, D. We said knowing that, we can just throw those values through this identity, this formula that we have. When we do that, we get this mess. But this mess reduces a lot. Reduces down to this. Well, this is just addition and subtraction now. So cleaning it up, we get 11 plus 2i, or I2 as I wrote it here. Now notice I say 2i or I2. They're equivalent. It doesn't matter how you multiply those. 2i and I2 are the same thing. Having said that, some quick background to all of this, because terminology is a little weird here. Back in the day, mathematicians knew about real numbers. Then we discovered the square root of -1. We're like, well, this thing doesn't act like a real number, so it must be an imaginary number. And then some guy came along, total tool, largely regarded as a bad idea, came along and was like, yo, I want to add a real number and an imaginary number. And everybody was like, yo, hold up, wait, let's not be extra. Dude, but it was like, no, bet it's going to be bay. Yes, I said bay. So he puts this real number in this complex number, in this imaginary number, and everybody looks at it and is like, bro, this looks complex. And it's stuck. Mathematicians, I don't actually know that is the exact story, but that is kind of how it worked out, right? We knew about real numbers first, and we're like, all right, bet, real numbers. These things will look like real things. Well, that must mean that anything that's not a real thing must be an imaginary thing. It's actually how that name convention came about. And then everybody saw, we developed complex numbers, and because it's more complex, we call it complex numbers. Mathematicians actually hate the naming convention here because complex numbers are actually way easier to work with in analysis than what real numbers are. I once had a professor describe complex analysis in a way that I'm not allowed to describe here. The words he said and used were certainly not PG-13, but needless to say, real analysis he described in the worst possible way. Complex analysis he described in the best possible way. And the reason why is because complex numbers are just easier to work with in the long run. So don't think of these as complex being hard. They're complex as in they've got a bunch of parts to them. That's all it means. Having said that, let's look at the second example. So the second example is going to be 4 times the complex number -2 plus 3i. Well, I could be extra and rewrite this as 4 plus I times 0 times the complex number -2 plus 3i. I could be extra and do that, but why? Why even bother with that? The imaginary part disappears. Anything that b touches disappears. All we're going to be left with is AC plus I times AD, which if we look, that's exactly what we would normally want to do here anyhow. We'd want to say, all right, 4 times -2 plus 4 times 3i. Let's do that. 4 times the complex number -2 plus 3i is going to be equal to 4 times -2 plus 4 times 3i. So this is going to come out to be -8 plus I12. -8 plus I12. Now you might notice I like to write my i's in front of the imaginary part. The reason why is so that the reader knows right away what they're looking at. They can say, all right, real part, real part, real part, up, imaginary part. Instead of having to go real part, real part, real part, number, imaginary, oh, this last thing was an imaginary number. Dope. So, this last example. 3 plus 2i times 3 minus 2i. Now I claim something special happens here. This number is special for a reason. And I'll talk about that in just a second. But we're going to go ahead and work it out without knowing that it's special. So 3 plus 2i times 3 minus 2i so A is equal to 3, B is equal to 2, C is equal to 3, D is equal to -2. Okay. With that, you know this whole thing is going to be equal to then 3 times, or A times C, it's going to be 3 times 3, that's 9, minus B times D, that's 2 times -2, that's -4, plus I times A times D. A is 3 times D is -2, so that's -6. B times C, that's 2 times 3, so that's +6. This whole thing is going to come out to be then 5 plus I 0, so it's just 5. And there's a typo in my math. I made a mistake. This is supposed to be +4 because it's -2 times 2. So, fixing my mistake, we have 13 plus I0, which is just 13. So this last value is going to come out to just 13. Now I said a second ago, something special occurs here. What's special about this is these two numbers are called complex conjugates. A complex conjugate is what I'm about to talk about in just a second here. All right, so complex conjugates, what are they? Well, let's say you're given a complex number a plus ib. Its complex conjugate is a minus ib. And let's say you're given a complex number a minus ib. Its complex conjugate is a plus ib. In other words, if you want to know the complex conjugate of a number, just flip the sign on the imaginary value, on the imaginary part. So as an example, let's look at these here. We've got 3 minus 4i. Well, the complex conjugate, I just said, you just flip the sign on the imaginary part. So the complex conjugate of 3 minus 4i is 3 plus 4i. Which means what we now have on the board is 4 i's because it's a pun. Aha! Dude, it's okay to laugh at my corny jokes. Thank you. That was funny. I don't even care. Anyhow, so in this next example, we want to find the complex conjugate of negative 5 minus I pi. Well, again, we just want to flip the sign on the imaginary part. Okay? So that's going to be negative 5 plus I pi. Okay, so that joke was really bad and I regret it, all right? There, I said it. Anyhow. This final example, we want to know what the complex conjugate of I times 13 is. Well, there's no real part, only an imaginary part. So can we take the complex conjugate of that? Sure, why not? Just think of the real part as being 0. In which case, the conjugate of this is going to be negative I times 13. So, a second ago, I said complex conjugates were special. Why is that? How is that? Well, let's see what happens when you multiply complex conjugates. Because that's the context with which I was talking, right? I said, when we were multiplying two complex conjugates, something special had happened. So let's see if we can see what it is here. I'm going to take these two values, a plus ib and a minus ib. I'm going to multiply them together. Okay, well, just like before, I'm going to use that whole FOILing thing. It's going to come out to be a times a minus ib plus ib times a minus ib Now we're going to go ahead and distribute through. This is going to come out to be a squared minus I times ab plus I times ba minus I squared b squared. Well, hey, look at those middle two terms. these two things are identical, right? But opposite. So they cancel out. This cancels with that. So all we're left with then is a squared minus I squared b squared. But I squared, that's just negative 1. So all of this becomes a squared plus b squared. And this is why complex conjugates are special. When we multiply complex conjugates, we will always end up with a squared plus b squared. Cool. So let's keep moving on then. All right. So let's imagine you were working on your web assigned homework, minding your own business, when suddenly, out of nowhere, I throw you this solution that comes out to be a fraction, but there's a complex number in your denominator. What do? Well, you can't leave the complex number in your denominator. That's not allowed. Mathematicians hate it. It's not okay. Don't put a complex number in your denominator. Don't leave it like that. It's bad juju. It is almost as bad as trying to divide by 0. Almost. So how are we going to handle it? How are we going to handle something like this? We got to get this complex number out of the denominator. What are we going to do? Well, just a minute ago we were talking about complex conjugates. And we saw that if we multiply two complex conjugates, it comes out to be a squared plus b squared. Well, that's a real number, right? There's no i's in there. It's just whatever the a was, square that, plus whatever the b was, square that. Well, wouldn't it be nice if we could use that here? Well, we can. We just have to know how to. The way to start is by multiplying this fraction by 1. Okay, so let's do that. Times 1. Well, I can rewrite that 1 however I want, right? I could, if I decided to, I wanted to rewrite it as a plus ib over c plus id times c minus id divided by c minus id. That's still 1, right? Right. Haven't changed anything. All I've done is I've rewritten our 1. And notice this 1 is now rewritten in terms of the complex conjugate of our original denominator. So when we go through all of this, what we're going to get out of here is going to be a new fraction, a plus ib, that quantity, times c minus id, all divided by c plus id multiplied by its complex conjugate. Well, again, we had a rule about that. We can simplify this a lot now. Now this just becomes a plus ib times c minus id divided by c squared plus d squared. And then we would also try to simplify the numerator. So the point of this is to say, if you're given a fraction with a complex number in the denominator, you need to multiply that fraction by 1. But it can't just be any 1. It has to be a 1 formed by the complex conjugate of the denominator of your original fraction. Then you can reduce it all the way down. You can get that complex number out of the denominator. It's a similar trick to when we had square roots in the denominator, right? Very similar idea. So let's use it here. What we've got in this example is 2 plus 3i divided by 4 minus 2i. Well, I want to multiply this by the complex conjugate, right? I want to multiply the denominator by the complex conjugate, that is. So what this is going to come out to be is going to be our original fraction multiplied by 4 plus 2i over 4 plus 2i. Okay. Well, that means this is going to come out to be 2 plus 3i, that quantity times 4 plus 2i over 16 plus 4 simplifying our numerator and our denominator now. We're going to have 8 plus 4i plus 12i plus 6i squared, all divided by 20, which is going to come out to be, grouping everything together and getting rid of this I squared, we're going to have 8 minus 6 plus I times 4 plus 12, all divided by 20. This is going to come out to be 2 plus I times 16 over 20, which we can reduce even further. Can break this up into two different fractions. 2 over 20 plus I times 16 over 20. Which is going to come out to be 1 over 10 plus I times 4 over 5. And that's it. That's all she wrote to that one. So let's keep moving on. So, really quickly, some more vocab. The principal square root of a negative number, in this case, negative a, is equal to I times the square root of a. So the square root of any negative value, we're just going to pull out that I and leave the square root of that value. Okay. Well, using that idea, let's figure out what these are. Let's put these back into standard form. In this first example, we've got negative 13 the square root times negative 4 the square root. Well, based on this is equal to I times the square root of 13 times I times the square root of 4. Or we can bring those i's together. We're going to get I squared. We can bring these square roots together. Square root 13 times the square root of 4. We can bring all that under the same radical, or we can go ahead and reduce this 4. What we're going to find, so this comes out to be -1 times 2 times the square root of 13. For this next example, we're going to do the same thing. We're going to pull out that I first. We're going to have I times the square root of 48 minus I times the square root of 27. Well, notice this is divisible by 4, this is divisible by 9, right? Both of those numbers are going to be square roots. Perfect squares. So we're going to get some cancellations coming out of this. Let's see what I mean. Here, let's actually divide this by 16. I have I times square root of 16 times 3 minus I times the square root of 9 times 3 . But we can break these radicals up now. We're going to get I times the square root of 16 times the square root of 3 minus I times the square root of 9 times the square root of 3. Well, 16 and 9 are both perfect squares. So what we're going to end up with then is I times 4 times the square root of 3 minus I times 3 times the square root of 3. Now we can pull out an I square root 3. We're going to be left with 4 minus 3 times I square root 3. I times the square root of 3 times 4 minus 3. This is just going to be I times the square root of 3. And for this last problem, we're going to pull out that I first. When we do, we're going to have -1 plus I times the square root of 3 times -1 minus I times the square root of 3 . Well, isn't that convenient? These are complex conjugates. So what that means is that all this is going to be is -1 squared plus the square root of 3 squared. Well, that's going to be 1 plus 3, or just 4. Cool. Well, that was convenient. So let's look at the next example. So before I let everybody go, I really quickly wanted to touch on these last two definitions, or these last two theorems, rather. So the first one we've got is the fundamental theorem of algebra, which basically just says that, if you got this polynomial, call it f of x, whatever, and it's of degree n, where n is greater than 0, then you're going to have at least one 0 in the complex number system. So what does that mean? Well, that means, say you got this crazy polynomial. Maybe it looks something like x to the 12th minus 14x cubed minus, or let's make it plus 7. Let's say this is your function. All this fundamental theorem tells us is you have at least one 0 in the complex number system. So what's a 0? Well, that's a very good question. I'm happy you asked. A 0 is just some value of x that when you put it into that, your function comes out to be 0 at the end. So whatever x value makes this whole thing equal to 0, it's called your 0. That's it. It's called a 0, I should say. Now, on the other hand, we've got this other theorem here called the linear factorization theorem. Basic idea of it is to say, so you've got this polynomial, f of x, it's of degree n, where degree n is greater than 0, then you have exactly n linear factors for that function. Okay, so what does that mean? That means here, for this function here, let's call this f of x, right? For that function there, you're going to have exactly 12 factors. Why is that? Because the degree of your polynomial here is 12. The degree is the power on your highest term. It's the highest power in your polynomial. It is the degree of your leading term. So, 12 here would mean you're going to have 12 linear factors. Precisely 12. What they are, who knows? Maybe they're the exact same factors. Maybe all 12 of those are the exact same. Why not? After all, x squared has exactly 2 factors. They're both 0. It's x and x. I mean to say it has 2 roots. They're both 0. So the linear factors would be x times x. Or let's say you're looking at, maybe another function you're looking at is g of x is equal to x squared minus 2x plus 1. This is exactly 2 factors. This factors out to be x minus 1 squared. So your 2 factors are x minus 1, x minus 1. Now before I let y'all go, I want to make a distinction. I want to make an observation here. These linear factors are written in terms of the zeros of your function. This g of x is only 0 when x is equal to 1. So somehow, this theorem and this theorem, they're related. We're going to look into that next class. Having said that, have a good one, everybody.